In this set of notes, we're going to look at some common discrete distributions. The first one we're going to look at is what is called the binomial distribution, or we could talk about binomial random variables. So consider these two motivating examples. So the first one we've seen before. It says, suppose that the American Heart Association claims that only 10% of adults over the age of 50 in the United States can pass the minimum physical fitness standards. And suppose we're going to select 4 adults at random who are over the age of 50 and give them a fitness test, and we're going to let y be the number that pass. So notice for this example, we're selecting a total of 4 adults, so we know how many we are selecting. We also know the probability of whether or not they pass. So notice there's 2 options here, either they pass or they don't pass. So we know the probability of passing is 10%, therefore the probability of not passing is 90%. And then our random variable is going to be the number out of those 4 that pass. Now for our second example, suppose we are going to randomly select 10 patients from UK Chandler Medical Center and ask each if they live in Fayette County or the surrounding counties. And again, we're going to let X be the number of patients who live in the region. So in this case, again, notice we know how many people we're going to select. We're going to select 10. For each of those people, there's one of 2 possible outcomes. In this case, it's either they live in the surrounding counties or they do not. And then again, we're going to look at the number out of those 10 that satisfy that condition. Both of these are what we call binomial experiments. So many experiments like these will have 2 possible outcomes, and some experiments also meet other criteria that quantify them as a binomial experiment. So a binomial experiment consists of n Bernoulli trials. And so a Bernoulli trial is any trial where there's only 2 possible outcomes. And so many situations are either exactly or approximately binomial experiments. So let's talk about what the characteristics of a binomial random variable are. So there's 5 characteristics that we need to meet. We need to have n identical trials. And each of those trials can only have 2 outcomes. And generically, we denote them as success and failure. For each of those trials, we need the probability of success to be the same. So for every single trial, the probability of success remains the same. We need those trials to be independent of one another. And we need the random variable that we're interested in to be the number of successes. Alright, so we're going to look at some examples. We're going to talk about how these 5 properties are or are not satisfied for these examples. And so the first one is the one that we've seen before with the American Heart Association. So let's look at it. So the first thing we need to satisfy is we need to make sure that we have n identical trials. Well, in this case, we're going to select 4 people. So each of those people are considered a trial. So n is equal to 4. And notice for each person, there's a 10% chance that they are going to pass the fitness test. So in this case, each of the 4 trials are identical. We need each of them to have 2 possible outcomes. And notice in this case, there are 2 possible outcomes. They are either pass or fail. 3, we need constant probability of success. And so notice that for each person that we select, they have a probability of a 10% or a 10% of passing. So in this case, we do have that constant probability of success, and p is equal to 10%. We need the trials to be independent of one another. So since we're selecting from a large group of people, we don't have any information selecting they're related to one another in any way, so it's fair to say that people act independent of one another. And then finally, the random variable we're interested in is the number of passes out of the 10. So yes, this is a binomial experiment. Alright, let's look at another example. So suppose that we have 10 blood samples sitting on a shelf. We know that 3 of the blood samples have been contaminated. We're going to draw 2 blood samples without replacement, so that's key there, to test to see if they are contaminated. Let contamination be a success. Is this a binomial experiment? So let's think about how this works. So I've got 10 vials on a shelf. And I know that 3 of them are contaminated. I just don't know which 3 they are. So let's say that the first vial I select is this one, and I find out, well, notice before selecting it, since I know 3 of the 10 are contaminated, there's a 3 out of 10 chance that the one I select will be one of the contaminated ones. So let's say that I select it and I test it, and I know that it is not contaminated. So I'm not replacing it, so I've removed it. So now when I go to select my second one, notice there's only 9 left to choose from. I still have 3 contaminated, so now my probability of selecting a contaminated one is 3 out of 9. So notice the probability of whether or not I select a contaminated one on the second trial is dependent on the first, and this is because of that without replacement. So let's talk about whether or not this one is going to be a binomial experiment. So the first thing we need are n identical trials. And I claim that this is violated. And the reason for it is when I choose the first vial, I'm choosing from 10. When I choose the second vial, since I'm sampling without replacement, I'm selecting from 9. And so in this case, these are not going to be identical trials. Do I have 2 possible outcomes? And the answer here is yes. We have contaminated or not contaminated. So that one was satisfied. We need the probability to be the same from trial to trial. But notice in this case the probability changes since we're sampling without replacement. Are the trials independent from one another? And the answer here is no, the trials are dependent, and we talked about that a moment ago. And then finally, y does equal the number of contaminated. So in this case, most of the properties we need for a binomial experiment are violated, and we're actually going to come back to this example later on, and we're going to see that this example actually follows a different distribution. Okay, and on our third example, it says if the probability that an infected person recovers from a certain disease is 0.2 and 10 people are infected with the disease, find the probability that all 10 of them recover. So for this one, we do meet all 5 requirements, and I'll let you confirm that on your own. So let's go through and see if we can find this probability. So n is going to be our number of trials. So notice we're selecting 10 people, so n is going to be equal to 10. P is our probability of success. So in order to define what P is, we need to make sure we define what our success is. So let's define the random variable x to be the number who recover. And we see that a person recovers from a certain disease with probability 0.2. So we can say that x is distributed as a binomial random variable with n is equal to 10 and p is equal to 20%. So we want to find the probability that x is equal to 10. Well, notice that this is the same as everybody recovering. So this is the probability the first person recovers, intersected with the probability the second person recovers, intersected all the way with the 10th person recovers. Now, since these trials are independent of one another, notice this is equal to the probability of R1 times the probability of R2 all the way to the probability of R10. And since each of the trials is identical, the probability of recovering for all of them is the same, and so this is going to be equal to 0.20 to the 10th power, which is approximately the following. So what if we wanted to find the probability that x was equal to 2, for example? Alright, so let's first start thinking about what this would look like in terms of who recovers. So if x is equal to 2, that means 2 out of my 10 people recovered. So it could be that person 1 recovered and person 2 recovered, and then everybody else did not recover. It could be that person 1 recovered, person 2 did not recover, and person 3 recovered, and then no one else did. And I could keep on going in this fashion, finding all the ways that 2 out of the 10 people recovered. In other words, I could say there are 10 choose 2 ways to place 2 recoveries. So if I wanted to find that probability, what I would say is the probability that x is equal to 2 is equal to, well, I know that I'm going to have 2 people who recovered, so I'm going to take my probability of recovering to the 2nd power. I know that there are going to be 8 people who do not recover, so I'm going to take that to the 8th power, the 0.8 to the 8th power. Again, this is just by coincidence that we have 2, 2, and 8, 8 here. Doesn't usually happen. But then I need to account for all the different ways that I could find those 2 people who recover out of the 8. And so we've got 10 choose 2 out here in the front. And this is how we could find the probability that 2 people out of the 10 recover. This actually gives us the formula for a binomial distribution. And so that's what we're going to see here on the next page. So a random variable y is said to have a binomial distribution based on n trials with probability of success p if and only if we have this distribution. And so let's diagram this equation down below and see what the different pieces represent. Our first term here, our binomial coefficient, what this does is this tells us the number of ways to place y successes in n trials. Our second term, what this is remember that p is the probability of success. So what we're doing here is we're taking p to the y power, where y is the number of successes. And the reason that we can do this relates back to that example we just looked at. Since we know the trials are independent of one another, we're multiplying the probability of those y successes against each other. And then our last term, q, well, q is equal to 1 minus p. In other words, it is the probability of a failure. And notice, if we have y successes, then we're going to have n minus y failures. So this term is doing the same thing as the one before, except it's accounting for the failures. So in general, we use this notation. We say that y is distributed. So we've got y is distributed binomial, and then we tell the number of trials and the probability. Now, just like for any other discrete random variable, if we sum over the sample space, we will find that that is equal to 1. And we saw that in the previous note set when we looked at discrete random variables. So let's look at another example here. And we saw this one earlier, and we already talked about how this one was not binomial. But let's see if the binomial can still be useful in a similar scenario. So suppose that we have 10 blood samples sitting on a shelf. We know that 3 have been contaminated. We're going to draw 2 blood samples without replacement and test to see if they are contaminated. Let contamination be a success. And we're going to find the probability that both of those are contaminated. So let's let y be equal to the number of contaminated. And we want the probability that y is equal to 2. In other words, we're going to draw 2 of them. We want to know the probability that both of them are contaminated. Well, notice this is going to be equal to the probability that the first one is contaminated intersected with the probability the second one is contaminated. And we can use conditional probability to help us out here because we know that these are not independent of one another. But what we can find is the probability of the first one being contaminated times the probability of the second one being contaminated given that the first one was. So for the first one, if we have 10 vials on the shelf, we know that 3 of them are contaminated. There's a 3 out of 10 chance that we choose a contaminated one. Now after we choose our first one, since we're sampling without replacement, we know there are 9 left on the shelf, and 2 of those remaining are contaminated. So the probability of choosing a contaminated on the second, given the first one was contaminated, is 2 out of 9. So this gives us a probability of 1 out of 15, which is approximately 0.0667. Now, as a general rule of thumb, if we suppose that each trial of an experiment can result in either a success or a failure, and that we sample from a population of size n without replacement, so similar to what we just did, if the sample size, in other words, the number of trials, is no more than 5% of the population size, then the experiment can be analyzed as though it were binomial. Okay? And so this is why when we're talking about populations, a lot of times we can model using a binomial even if we have sampling without replacement. So let's look at that example again. But now we're going to increase our numbers. So now suppose that I've got 1,000 blood samples and I know that 300 of them have been contaminated. Again, I'm going to choose 2 without replacement to test to see if they are contaminated. Alright, so we're going to do the same thing that we did before. So we could solve this the same way. So the probability that y is equal to 2, we know that's equal to the probability the first one's contaminated intersected with the second one, which is equal to the probability of the first one being contaminated times the probability of the second one being contaminated given the first one was. And now, notice the probability of the first one being contaminated is equal to 300 divided by 1,000. And for the second one, we have 299 divided by 999. Which is approximately equal to 0.09. Now, notice here that n is equal to 2. And obviously 10 is no more than 5% of 1,000. So we've actually satisfied this rule of thumb. So let's see what happens if we were to use a binomial instead. So notice that for the first bulb, we had a 300 out of 1,000 chance of being contaminated, which is approximately 0.3. And for the second bulb, we had a 299 out of 999 chance of being contaminated, which is again approximately 0.3. So notice from one trial to the next, we have approximately the same probability of success. So we could use a binomial where we have n is equal to 2 and p is equal to 0.3, let's see what answer we get. So if we want to find the probability that y is equal to 3, notice this is going to be equal to choose 2 times 0.3 to the second times 0.7 to the 0, which is equal to 0.09. So in cases like this, we could calculate the probability directly, or we can use the binomial, and we're going to get very similar answers. Now, notice this fact did have that without replacement. So here's another fact. If we have with replacement, then we will always have a binomial. Now there are many ways to compute these. We could use the formula that we just saw. You can also use a calculator, software. There's even tables. We'll be using R in this class, and so here are the commands for if we wanted to use R to find those probabilities. Right. We also have the mean and the variance and standard deviation for a binomial random variable, and here are those different formulas. Let's work with that example that we saw before, and so we can find some different probabilities as well as the mean and the variance. Alright, so again we're supposing that the American Heart Association claims that only 10% of adults over the age of 50 in the United States can pass the minimal physical fitness standards. So suppose we're going to select 10 adults at random who are over the age of 50 and give them the fitness test. We're going to let Y be the number who pass. So first we want to find the probability that exactly 3 pass. So this is the probability that capital Y is equal to 3. Using our formula from before, we need to figure out the different ways that we could. Next, we need to account for the fact that there were 3 who passed, and we know the probability of passing is equal to 0.1, so we take that to the third power. So then that means that 7 did not pass, and the probability of failing is 0.9. And you could put this in your calculator, and you would find this is equal to 0.0574. Now alternatively, instead of your calculator, you could use the binomial function in R, and that would be d binom. We're interested in Y equal to 3. We have 10 trials, and the probability of success is 0.1. And this will give you the same answer. Find the probability that at least 2 pass. So this means the probability of Y being greater than or equal to 2. Because if we have at least 2 pass, that means we could have 2, 3, 4, 5, all the way up to 10. Now, in order to calculate this, let's think about what a number line would look like for our potential answers. So Y could be equal to any number from 0 to 10. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and I realize they should be spaced better. But if we're interested, and let's put those numbers below. If we're interested in the probability that Y is greater than or equal to 2, so notice that would encompass all of these numbers. So the complement would be Y less than or equal to 1. So in this case, it's actually easier to calculate the complement, so we know that this is equal to 1 minus the probability of the complement. Now, anytime that we've got the random variable less than or equal to some number, we call this a cumulative probability. And so in this case, notice this would be equal to 1 minus, and that's the probability that Y is equal to 0, plus the probability that Y is equal to 1. And to find those probabilities, we could fill out our formula for both 0 and 1, or we could use R to help us out. So R can help us find cumulative probabilities using the p binom function. So in this case in R, we would do 1 minus p binom. And now the value that we're interested in is 1. We have 10 trials, and probability of success is equal to 1. And if you put this in R, you'll find this is equal to 0.2639. Okay, find the probability that at most 3 pass. So this is going to be equal to the probability that Y is less than or equal to 3. And so again, we could use our formula and find the probability that Y is equal to 0, plus the probability that Y is equal to 1, plus the probability that Y is equal to 2, plus the probability that Y is equal to 3. Or, since this is again a cumulative probability, we could use the p binom function in R. And so this time for p binom, we're interested in 3 successes. We still have 10 trials and probability of success is 0.1. We could also find the mean and the variance of the number that pass. So recall that the mean for a binomial random variable is equal to n times p. So in this case, n is equal to 10 and p is equal to 0.1. So this is equal to 1. So what we're saying here, on average, out of 10 people, we expect 1 to pass. And then for our variance, we have n times p times 1 minus p. So here we're going to have 10 times 0.1 times 0.9, so we get 0.9. And then of course if we wanted to find the standard deviation, we could take the square root of the variance. So there are many other types of discrete random variables, and so the next one we're going to look at is what is called the geometric random variable. It's very similar to the binomial. We're still going to have independent identical trials. Each trial will still result in a success or failure. But now what's going to be different is instead of modeling the number of successes, we're going to model when the first success occurs. So a random variable y is said to have the geometric probability distribution if we have the following. And so just like before, let's kind of diagram what's happening down below. So here, the idea is that we're going to have different trials. So you can imagine each one of these is a trial, and we are going to stop with first success. So notice we could stop on the first one, the second one, the third one, and so on. So notice the smallest value we can have with the geometric is 1, and so you'll notice that the smallest value y can take is 1. And notice wherever we stop, so whichever y we stop on, there will always be below it y minus 1 failures. So for example, if we stop on the 5th, there will be 4 failures. If we stopped on the 6th, there would be 5 failures, and so on. So notice we can look at our equation as 2 different pieces. The first piece accounts for the y minus 1 failures. The p by itself, that is the first success. Just like with a binomial, we can find the mean and the standard deviation, and here are those formulas. So let's look at an example of what a geometric random variable would look like. A representative from the University of Kentucky Football Marketing Division randomly selects people on a random street in Lexington, Kentucky until he finds a person who has attended a home football game in the last 2 years. So notice we're going to keep on talking to people until we find a person who has been to that home football game in the last 2 years. Let p be the probability he succeeds in finding such a person, and we're going to say it's 0.30, and we're going to let x denote the number of people he selects until he finds the first success. So what is the probability that the first person who has attended a home game in the last 2 years is the first person selected? So in other words, what is the probability that x is equal to 1? Well, notice that for each person we talk to, there's a 0.3 probability that they're a success, and in this case a 0.7 that they are a failure. So we could go up to our formula, and we could say, okay, well, the probability that y is equal to 1, that's going to be q to the 1 minus 1, which is 0, so that cancels out, that's just a 1, times p, or our success probability. So in this case, this is equal to 0.30. The other way to think of this is we only talk to one person. There's a 30% chance of success on that first person, so there's a 30% chance that we stop after the first person. What is the probability that the first person who has attended a home game in the last 2 years is the third person selected? Well, again, so if they are the third person selected, that means that the first 2 were failures, and my third one was the success. So what that tells me in terms of thinking of the equation, my probability of failure is 0.7, and there were 2 failures followed by my final success. What is the probability the first person who has attended a home game in the last 2 years is the 10th person? Well, we can do something very similar. We know that the first 9 people we spoke with are failures, and the last one is the success. We could also find the mean and the variance for this random variable. So for the geometric random variable, the mean is equal to 1 over p, the probability of success. So what this tells me is, on average, I'm going to have to speak to 3.3 people before I find a success. And again, recognizing you can't actually speak to 3.3 people, it's just this is what happens on average. And then for our variance, we have the following. And then just like with the binomial, we could use R to calculate these probabilities as well. So notice the first one is going to give us the probability that our random variable is equal to a specific number. The second one is going to give us cumulative probabilities. So this concludes this note set. In the next one, we're going to look at some more common discrete random variables.